Welcome to the College Knowledge Podcast, sponsored by the College Planning Network and Paradigm Financial Group. Whether you're searching for that right fit college, applying to college, or figuring out how you're going to afford it all, you're in the right place. You'll hear from deans, admissions counselors, student athletes, and scholars from esteemed universities and colleges around the country. We'll dig deep to uncover their insight and unique experiences. So whether you're a student gearing up for college or a parent with college-bound kids, sit back, relax, and listen. Like you, we have lots of questions. Our guests have the answers, and we're excited to share them with you. Let's get started. Here at Elite Collegiate Planning, we're able to send students to private schools for nearly a fraction of the cost of public schools. Visit our website, elitecollegiateplanning.com, to learn more. Hey, everybody. Welcome back to College Knowledge. I'm your host, Dave Kozak, alongside my co-host, Mr. Joe Kearns. Good morning, Joe.
Good day, Dave.
And today we have the distinguished pleasure of interviewing Professor W. Nielsen Brandt, the Eberly Chair Professor of Astronomy and Astrophysics from the Pennsylvania State University. Professor Brandt, welcome to the show, and thanks for joining us.
Great. Thank you for having me.
So I think the big thing that we always like to get out of the way early is kind of give us your experience of how you got to where you are being a professor of astronomy and astrophysics at Penn State, and just kind of your journey to where you are today.
Okay. Well, I always liked science since I was a little kid.
Okay.
I always liked especially space. You know, back when I was in elementary school, I really didn't fully understand what that meant, but I, read textbooks, books from the library and so on these things. Then I worked very hard in high school and got admitted to a good undergraduate institution. I went to Caltech. And at that point, I was very excited about particle physics, which had made tremendous advances in the 1950s and 60s and 70s. And I was an undergraduate starting in the 1980s.
Okay.
And I came to appreciate after I learned more about what was actually going on today, rather than what you read about in a book, which is usually a decade or 2 decades behind, that what really seemed exciting was astrophysics. A lot of the great advances of particle physics had been made already. And astrophysics was still opening up to a great extent. And so I did undergraduate research. I studied solar astronomy. I studied then the cosmic microwave background, and that got me hooked on astronomy. And then I went off to graduate school and got into X-ray astronomy, which I really didn't know at the time, but was a very good strategic choice. It wasn't something I had a master plan for or anything. I just kind of happened to go in a direction that was very good. A reason why it was very good is that NASA was going to be launching the Chandra X-ray Observatory, which is a several billion-dollar space mission that studies X-rays from the universe. And I happened to be very well timed in the sense that I was finishing graduate school and in a postdoctoral position just as Chandra was going to go. And so I was able to very fortunately get hired at Penn State as an assistant professor with the opportunity of working on the early data from the Chandra X-ray Observatory, which is still going great now, 24 some years later.
Wow.
So that's kind of how I got here. While at Penn State, I've now spent, I guess, about half of my life at Penn State. The Chandra X-ray Observatory thankfully was built to last. And so great data continue to come in year after year after year. And it's been that way since it launched in 1999.
Wow.
Yeah. So that's kind of the train that I rode through the professor years, to be successful. Clearly, I worked on a lot of other data as well, from the XMM Newton Observatory, from the New Star Observatory, and from other wavelength observatories as well. But that was kind of the core of how things got to the way they are. Yep.
So one of the themes that comes up a lot as we're talking to different professors and really business owners and all of the different people that we've interviewed is mentors, and this idea that there are people that help throughout your journey to kind of propel you in a direction. Did you have that same experience of mentors kind of helping you pick directions and make moves, or was it more serendipitous?
Well, okay, so yeah, I did have very good mentors for whom I am thankful, both when I was an undergraduate and when I was a graduate student. That being said, my actual choices of directions, those were not. I did not get a lot of mentoring on those. Like when I chose to go into X-ray astronomy, I'll just give you an example. I thought when I went off to graduate school, I might continue working on the cosmic microwave background, something I had studied when I was an undergraduate, which is kind of radio astronomy type science. Then when I arrived in Britain to start my PhD, they have a very different approach than we have in the US, where pretty much you show up and the next week you start working on your thesis. So you have like a week to make a very important decision. And I just kind of looked around and saw what looked exciting to me at the time, and saw who I resonated with personally, in conversations as to who might be my PhD advisor. And thankfully, and this was not something I received mentoring on, but just thankfully, I happened to choose something that was a winner. In the sense that I mentioned, Chandra X-ray Observatory was coming along. There was going to be a great need for people that were trained in this particular area, so it happened to work out. But that was mostly luck. I did receive good mentoring and good advice, but some of these big decisions, I could have benefited from better mentoring, although fortunately for me, I made good choices. Some of my other friends who made, also what appeared at the time good choices didn't work out as well in the long term.
Yeah. And I think it sounds like you also worked hard, and they always say that hard work produces better luck than not working hard, right?
Sure.
So for clarity, you said astrophysics became kind of your in undergrad, you enjoyed that subject matter. Can you elaborate for us what astrophysics is?
Oh, sure. So it's the study of the universe overall, ranging from stars and planets through to galaxies and cosmic structures and supermassive black holes, through to studying the entire universe, as a cosmological entity. All of that falls under the area of astrophysics. Yeah.
Okay. And how much, there's this concept in my brain that the universe is infinite, and it may or may not be, but if that's the case, then we have an infinite amount to learn at the same time. How much do we know about the universe today?
We've made enormous progress over the past several decades. We aren't at the level of particle physics now, where they have a standard model that has been super precision tested to many significant figures, and they pretty much have the answers for not everything, but a heck of a lot. We're not quite there yet, but we are getting there. We have conducted enormous surveys, very powerful, at a wide variety of wavelengths that have told us, very fundamental things about the universe's expansion, about the components of the universe, given us insights into what the universe was like at very early times. We also understand broadly the population of objects out in the universe. There are galaxies and supermassive black holes out in the distant universe, lots of stars and planets in our galaxy and gas. And we have a pretty good now census, we think, of what's out there in the universe. Now, I hope I'm wrong. I hope we'll be surprised and that there's some fundamentally new thing out there that we have yet to discover, that we will discover. That would be tremendously exciting. If I had to place a bet, given my 30 years of experience now playing the game, I have to say, I bet we've mined the universe well enough that we know what's out there. And I hope I'm wrong. I hope there's some amazing new surprise, some new type of cosmic object we have yet to discover. But so far, as we've expanded our surveys more and more powerfully out into the more distant universe, we find more and more of the things we've already known about now. And that has been a fundamental change. 20 years ago, I don't think I could have said that with the same level of confidence at all. We had not surveyed the universe so impressively thoroughly as we have now. Yeah.
So where where does it go from here? Is it refining, as you said in the particle physics? They've refined it down to these. Are we now in the refining state?
I hope
of
not.
understanding?
I hope we're not. Yeah, that's what I'm saying. I was kind of alluding to. There still are big fundamental questions out there. That we are wrestling with. But in terms of the broad strokes of what's out there in the universe, I mean, what are the ingredients we have to play with? We think we know what those are. Exactly how you put those together in a recipe to make the universe that we find, that is where we still need improvement. And there are a variety of things there I could mention. What is the dark matter out there in the universe? You've probably heard that there's a lot of dark matter out in the universe. We still don't really understand what that is. Other things, why is the universe expanding the way that it is? Exactly how have black holes grown? How have they interacted with the galaxies in which they reside? Those are examples. Is there life out in the universe? Those are big questions that are still out there, still to be answered. But again, regarding what basic ingredients do you have to work with on the table, we think we know what the ingredients are.
Okay. And you said you kind of got down this way because you love science and you sort of became very focused on space and that whole thing.
Yep.
In your, again, thinking of our audience, the students and parents that are pursuing higher education, what can a student expect to study on a course towards obviously astronomy? I think there's a general knowledge of astronomy, which is the study of stars and space and all that.
Right.
What types of classes are they taking? What's the rigor of the curriculum? How much is it focused in science and math versus, thought and things like that? Can you just kind of lay that out?
So that will vary from place to place.
Okay.
For students who want to go into research astrophysics, a research astrophysics career like what I've done.
Okay.
It's quite rigorous. We do not spend a lot of time teaching our astrophysics majors, the pretty constellations up in the sky, and let's philosophically appreciate the wonder of the universe. There's not a lot of that. It's hardcore math and physics type approaches to things. That's how we do it.
Okay.
So what undergrads, my best advice for what undergrads would want to study, clearly studying, a lot of astronomy, astrophysics, a lot of just hardcore basic physics they should study. They should be pretty good at math. You don't need some of the super fancy mathematical techniques so much, at least so far in astrophysics, although they can be useful often. And so the obvious things, like I said, astronomy, physics, and math. But then in addition, there are a number of other skills which aren't always appreciated. One of them is just being really good with computers and coding.
Okay.
So not just playing Minecraft, but really, being able to write code, to solve problems. That's extremely valuable. Another very important skill, which people can learn, but they usually don't early in their career, is just good practical statistics. We're usually modeling complex physical systems, and how do you test models with data? What is the statistically powerful and effective ways to do that? There's a tremendous amount of knowledge there that oftentimes, unfortunately, is not often taught to people. And then other things. Writing is an extremely valuable skill even in science. We're not all just cranking out numbers. I mean, ultimately you have to be able to write, interesting papers that show people what you've discovered and tell them why they should care. So they bother to read your paper, and you have to be able to write convincing proposals. We are able to conduct these scientific projects by winning proposals that give us time on observatories like the Hubble Space Telescope or the Chandra X-ray Observatory, or money to conduct research. And there is a significant element of just, can you write well? Can you write a convincing proposal? Those are types of things. Those are just basic skills. And sadly, many people develop their ability to write, and that harms them for the rest of their career.
And I would extrapolate on that it is not unique to any particular subject matter, if you can write and communicate the subject matter that you are studying or you are presenting on, your effectiveness in life is tenfold what it would be if you cannot put it on paper, write it, and communicate it to people.
I agree with that broadly. Yeah, I mean, I sometimes tell my students that if you cannot write really well, you're always going to work for someone else.
100%.
Yeah,
without question.
That's just the way it is. I mean, those are some basic skills. So like I said, additional things: coding, practical kind of street fighting statistics that you actually use to solve real problems, and writing. Those are some very important skills to develop as well early on, and that students in high school can develop if they want to. Yep.
And I think that's a key point you make if they want to. One of the things that I've been disappointed with across the board is the focus on that type of stuff at the high school level, the requirements to become a good writer and to actually practice that. And I think it's the last few years have been very difficult in that regard for students. And I think the way communication happens now, the texting and the Facebooking, and nothing's a thorough thought from start to finish. You don't get your introduction, your body, and your conclusion and anything. It's just these, it's shortcuts to everything, right?
Yep.
So
that the students unfortunately are not developing their ability to do long form writing. Yeah.
No.
Yeah,
emojis don't count.
No,
emojis don't.
Doesn't help that much.
So
we don't use emojis in our proposals.
No, certainly not. And then if you do, you're not getting the money or the time.
That's right. Yeah.
In your under these majors that you teach and kind of preside over, how many of the students go on to postgraduate work versus enter into the workforce from your experience?
Okay, well, so there's a number of ways I could answer that. So let's consider the students who major in astronomy and astrophysics in our program.
Okay.
My rough estimate, and again, I'd want to check the numbers to be sure, but probably about 50-50.
Okay.
About 50-50. I mean, there are many valuable things that students who decide after a while that they really decide that they're not up for a research career. Either they don't like it, or it's just not for them for one reason or another. There are very valuable things they can do. We have students go off and become telescope operators at leading astronomical facilities around the world. We have students become high school teachers, and these can be superb high school teachers and can help other students in their journeys. So I would say again about 50-50, and we try to make it so that all the students have a good outcome in the long term. We don't just somehow care about only the ones who are, headed for the high strung research astrophysics track and kind of ignore all the others. We try to make sure everybody has, good opportunities.
And I mean, again, I'm assuming this, as we've found with many of the discussions we've had, there's crossover necessary in all different genres where this kind of education is applicable. I mean, I would imagine in what the SpaceX and the what all of them are doing are requiring this type of knowledge to produce the rockets, the ships, the anything that's going to go out there, because we're working on, as you said, kind of, we know the ingredients, and so you got to be able to fight the ingredients that we know about.
I think that's
I would imagine
right.
Boeing and Lockheed and all the. And I would also imagine, and correct me if I'm wrong, but there's probably a substantial amount of government jobs available in this arena as well.
In fact, I've had people in my group, even who have been graduate students or even postdoctoral researchers, who go off and work in the aerospace industry afterward.
Okay. Yeah.
Some of them probably have salaries higher than mine.
Wow. And isn't that the case sometimes, right? So first of all, this is the question I have to ask, because I'm reading an article last night and it was discussing that the government is opening up or they're declassifying UFO documents and they're putting it out there.
Yep.
You've seen, you've been, you've looked.
Yep.
Are we alone or not?
Well, okay. So there's a couple.
And you don't have to answer it factually. You can answer.
There's a couple of ways I'll answer that. Okay. first of all, do I think we're alone in the universe? Probably not.
Okay.
Now, are we being visited by aliens right now? Well, I don't know for sure. I have skepticism.
Okay.
Extraordinary claims require extraordinary evidence. I have seen interesting things, but nothing that rise to the level of extraordinary evidence right now.
Okay.
So that's the way I would answer it. I'm open-minded. I mean, people are saying they're seeing strange things, and apparently, I mean, again, I haven't directly spoken with these people, so I don't have primary source knowledge.
Mm-hmm.
Yep.
But you know what I read in the newspapers are the same types of things that you read. I mean, that military pilots have seen remarkable things they can't understand, and some of these have been captured on radar. So there are something strange seems to be going on. But again, I haven't been able to speak with the people who are making these claims to critically cross-examine them myself. So I'm interested but skeptical. That's the way I would phrase that. You know, regarding the Earth. You know, again, the universe is so big that out there in the whole universe, there probably are huge numbers of civilizations, most of which are unable to communicate with us and probably never will be able to.
Got it.
I mean, you know, if you just look at the number of galaxies out in the universe, you know, the types of things that could actually interact with us, as far as we understand, would be things in our own galaxy. But, you know, you have to remember there's 100 billion galaxies out in the universe.
Yeah.
So, and anyway, the numbers are such that it seems very likely that there are other civilizations out there, but whether they are around close enough to us, they can actually contact us. Well, that's still an open question. I think it's possible, but regarding visiting Earth and all these things, I am not yet convinced.
Okay.
But I'm willing to consider the evidence, but it's going to have to be extraordinary evidence.
Well, I mean, and if you think about evolution of mankind, essentially, or the human being, right?
Yep.
It's taken us an incredibly long time to get to just the beginning of space, let alone the extensive expanse of space. So
yes,
they would have to be advancing more rapidly and have either been around longer or just are smarter or more well equipped for that type of thing.
That's right. Yes. And just two other points I'll mention. First, you know, NASA, for example, is taking this quite seriously. There is a high level NASA panel right now that is looking at the evidence. You know, I am not on that panel, so I am not spending a significant fraction of my time critically digging into all those claims, but I will be very interested to see what they come up with.
Got it.
That's one point. The second point, then, regarding search for life out in the universe more generally, I mean, people do take that very seriously. We have a professor here at Penn State who has, over the past couple of years, transitioned to a research program where he spends a significant fraction of his time working on SETI, the search for extraterrestrial intelligence. You know, I personally view it as a long shot bet, but, you know, if you hit the jackpot, then you've made one of the biggest discoveries ever.
Yeah.
And so, you know, we'll have to see how that pans out.
Yeah.
So, and this may be outside your expertise, but I feel inspired to ask.
Sure.
How far and maybe it's not because you're engaged in some of the technology that we have in space right now. How far are we from actually being able to explore legitimately space?
Explore it? You mean like by physically going there?
Yeah, well, you know, the Star Trek.
Well, Star Trek is a long way away indeed, and probably the laws of physics prevent Star Trek in some respects. But we are making, as a civilization, we're making remarkably rapid progress. But you know, the challenges are daunting. Okay.
Yeah.
You know, even the closest stars, remember, are light years away. That means even if you can accelerate a vehicle to, say, 1/10 the speed of light, which is a very, very challenging thing to do, you're talking a 40-year journey just to get there.
Got it.
Okay. Unless there's a warp drive or something, which I am skeptical.
Fingers are crossed.
Yeah, fingers are crossed. So this is going to be just sending a robotic probe to another star system. I mean, you're talking about probably a 100-year endeavor.
Wow.
You know, building it, designing it, and then actually, waiting for the travel time. It's going to take 40 years just to travel there. So this is going to be a longer term endeavor. Now, again, though, on the span of humanity's existence on Earth, that still is a rather short time. And, technology is advancing very rapidly. Especially some of the developments in AI, which already are starting, I expect them to be quite spectacular. We may soon have, computing systems that in some respects, they're not the same as people, but in some respects will be 100 times more capable than people. Yeah. And so then with those types of things, you could imagine developing systems that could be very effective at exploring the universe. So, I don't know, several hundred years, 1,000 years, we could then have started to explore by actually going to, places, in the relatively local patch of our galaxy, which is pretty impressive. But remember, our galaxy is enormous. It takes of order 100,000 years for light to travel across our galaxy. So, just colonizing our galaxy, that's going to be many, many millions of years just due to the light travel time alone, let alone all the other challenges.
Well, it's interesting because we did an interview of a group of students. I think it was a combined project between Rutgers, Drexel, and I forget the third school. Do you recall? It was called the Rascal program. I think it was Temple.
Okay.
And it was a group of engineers that were tasked in this competition to figure out the scenario they were given was they had landed essentially a spaceship on Mars. And their job was to do the engineering to get the craft off of Mars back into orbit, headed back to Earth. And it was just in them talking about the fuel sourcing and the amount of thrust necessary and the angle, and you start to realize that the spacecraft's ability to withstand the heat and the changes in temperature and the timetable and all that. You start putting that stuff together and you think about the fuels that we're using, like we're not even close on a lot of that. But I've also watched the program about the rovers, the Mars rovers, where we did land them and they did explore and we've seen stuff. So that is in the last 20 years, right?
That's right. Yeah. So we are making remarkable progress, but don't expect Star Trek, by the time, while we're alive, it's just not going to happen. And many aspects of Star Trek, I think, are just never going to happen because they violate laws of physics. We understand them. Yeah. But anyway, I don't know, 1,000 years, something like that. Well, that's at least conceivable.
Yeah. All right. A couple of things. Whenever we talk with professors or different areas, there are so many misunderstandings, myths when it just surrounds college or a specific field of studies. If students are saying, hey, mom, dad, I want to, study astronomy, astrophysics, and mom and dad's experience as somebody like me, that it is Star Trek, Star Wars. That's the only experience I might have ever heard of a black hole before.
Right.
What are probably some of the biggest misconceptions or just assumptions about the field that are just flat out wrong that people may assume that they need to know it's not exactly? What have you seen?
So
students essentially assume
again, that we sometimes even still have students coming in where they think astronomy is kind of the artistic appreciation of the universe and constellations and all that, and that's not what you're going to get in a research department doing astrophysics. So that's one misconception. And then, as you said, even though there is an abundance of actual reliable information out there now, much more than I had available back when I was a student, there still is there's large amounts of misinformation where, as you say, students somehow think that Star Trek or Star Wars is a realistic possibility or something, and it's just not. Now, the students, most students don't have those misconceptions. Some of them do, and they normally self-correct quite rapidly. Even very smart people sometimes have those misconceptions. So those are some challenges. Again, I don't really talk to the students at the level where I know deeply other aspects of their lives. I just, I'm pretty straight focused on, physics and math and astronomy and, coding and statistics and so on. So I haven't really probed other aspects, other possible misconceptions that deeply. It's not my job. And so I don't do it.
If you didn't know, we're on Instagram, Facebook, Twitter, and LinkedIn at Elite Collegiate Planning. Make sure to share and tag us. So obviously you've done a substantial amount of research in your 30 years on the subject matter.
Yeah. Yes.
There's black holes.
Yes.
Are something that I remember when I was young. My dad was a chemist and a intellectual property attorney.
Okay.
And he was working in the chemical industry. And for whatever reason, science, obviously chemistry, obviously, he was excited about this. And we watched this movie on black holes. I mean, I was probably 10. And the idea was black holes will basically swallow the universe. What really is a black hole, and why are they important to study, and where is that research going? And I have a follow up to that.
Sure. I could say a lot on that. So how about this? I'll start off and then guide me along with some additional questions. Sure. So we end up answering what you want to know. So black holes are made when a massive star, a star typically with more than, say, 20 times or so the mass of our sun, comes to its end, and the core of one of those stars crunches itself down, squeezing itself down to where it becomes smaller than the Earth, smaller than the size of the city you're in, smaller than the room you're in, smaller than a baseball, smaller than a speck of dust, squeezes itself all the way down effectively to being a point. That's what a black hole is. It's the core of a star. It starts off as a star that has a core collapse, and the core crunches itself down essentially to a point. And if you could fly up and look at one of these black holes out in space, you would see a black sphere. There's a region close to this crunched down thing from which light cannot escape. And this black sphere is what people generally think of as a black hole. Now, again, this is another place where there are misconceptions. Often in Star Trek, sometimes and other shows, you sometimes see black holes portrayed as a kind of whirlpool out in space. They are not a whirlpool. They don't have some magic sucking power like a cosmic vacuum cleaner. They attract things, but they attract things via just normal gravity. Okay. They just pull in stuff via normal gravity. They have a lot of mass, so they do have a lot of gravity, but they don't have some magical sucking power or anything like that. Now, these black holes, once they are formed, can continue to grow. They do pull in matter via their gravity, and each time a black hole eats a kilogram's worth of matter, its mass grows by a kilogram. And so black holes can grow over time by eating material. Some black holes, the ones in the centers of galaxies, in fact, have grown enormously. We know, for example, that there is a 4 million solar mass black hole sitting in the middle of our own galaxy. Our best understanding is this black hole started off billions of years ago, with about, 10, 15 times the mass of the sun. We don't exactly know, but somewhere in that ballpark. And then over billions of years, that black hole, via its gravity, pulled in material, grew and grew and grew, all the way from 10 to 15 times the mass of the sun up to 4 million times the mass of the sun. That's called a supermassive black hole. And then if we look out into the universe, we actually find objects that are much more massive still. We have found examples of black holes that are 1,000 times more massive than the supermassive black hole in our own galaxy.
Wow.
And so instead of being 4 million times the mass of the sun, they're 4 billion times the mass of the sun. And in fact, the most massive ones we found go up to about 20 billion times the mass of the sun. So there are these monstrous black holes out in the universe. Now, then I think you also asked, why do you care? Why do you care about this? Well, these are a fundamental prediction of Einstein's theory of general relativity. So they're interesting in a basic physics sense to make sure that we really understand the nature of gravity. That's one reason they're important. They also Our excellent laboratories for extreme physical processes in the universe, matter that gets close to one of these black holes is subjected to very strong gravity. It is induced to move at a large fraction of the speed of light. Remarkable things can happen to matter under that scenario, in that regime. And I can say more about those if you're interested, but that's a whole nother reason. Kind of laboratories for extreme physics. That's another reason why black holes are important. And then finally, we have come to appreciate over the past couple of decades that black holes likely had a significant role in shaping what galaxies are like. Mm-hmm. Okay, that black holes are not just kind of nice Christmas tree ornaments present in galaxies, but they actually have something to do with how galaxies put themselves together. And then there are finally some more speculative ideas suggesting that universes and black holes may be significantly related, and that we may be living in a black hole in a sense. And I can elaborate on that later. Well, that's more speculative, but those are examples of reasons why black holes are important. Understanding the fundamental nature of gravity, space, and time, extreme laboratories in the universe, shaping galaxies, and then perhaps even broader cosmological connections.
Yeah. So my question is, as a layman here, hearing all this, right?
Yep.
Just being simple in my elementary understanding of gravity. If what you're saying, these black holes that are masses larger than the sun, and there are a lot of them out there, right? Mm-hmm. And there's one in our galaxy.
Yes.
Would that not be then the gravitational pull that holds the whole thing together?
Right. That's a good question. And the answer is no, it is not. Huh. Okay. So let's consider just our galaxy. Yeah. Okay. Our galaxy, if you look at what makes our galaxy, the things that we normally think of are all the nice stars in the galaxy.
Yeah.
Of which there are about a ballpark 100 million stars in our galaxy. Okay. Our sun is not a wildly atypical star, so just the stellar mass of our galaxy is of order 100 million times the mass of the sun. Okay. Then you have all the other constituents of our galaxy, most impressively the dark matter, which actually makes up probably 10 times more than all the stars. Okay. And so while that 4 million solar mass black hole in the center is a very impressive object, it is a fly compared to the elephant of our whole galaxy. So if we do believe that black holes affect galaxies, but it is not right to think of a galaxy as kind of being a galaxy kind of swirling around the black hole. It is not that sense. Most of the galaxy, 99% plus of the galaxy, doesn't even know that black hole's there. And if you could somehow magically snap your fingers and make that black hole go away, the galaxy would go on doing its business, hardly noticing it was gone, until some of these other effects that I've alluded to and can talk about more would come into play.
So then and again, excuse my infinitesimal knowledge here, but
that's fine. No problem.
As a singular structure, we'll call it, in the galaxy.
Yeah.
Is it larger than the other singular structures, like a singular star or a singular planet?
Yes, good question. Yes, so we know how big these black holes will be, given their mass. Here's a simple rule. If you want to sort of know the simple way I remember it, typically you get about 3 kilometers, and so you get about 3 kilometers in radius per solar mass of mass. So a black hole that is 1 times the mass of our sun would have a radius of about 3 kilometers. So that 4 million solar mass black hole in the center of our galaxy has a radius of about 12 million kilometers. That's about 10, 15 times the radius of our sun. And so that black hole is not stupendously large. I mean, 10, 15 times the radius of our sun. It would comfortably fit in the inner solar system. In which we live. I mean, it would fit it, probably inside Mercury's orbit around there. So these are not fantastically large. And the reason why you have so much mass yet it's not so big. Well, that's because the density is very high. A black hole is the ultimate compressing down of matter. You have a lot of matter compressed down into a small space. So, these black holes, compared to other structures in our galaxy, I think you asked about that. We know of individual stars that during their evolution swell up and become enormous. And these are substantially bigger than the black hole in the center of our galaxy, even though their mass is much less.
Okay.
Yeah.
And what I wrote on my paper, I wrote slingshot. And this is how my brain works. I don't know.
Well, what do you mean by slingshot? I can say something about slingshot
in NASCAR, right? And I'm not a big NASCAR fan, but you slingshot around someone. This probably comes from Days of Thunder or Ricky Bobby. I don't know. But though you get the tail and you get on the tail, you get the wind, and you can get some pulling around. Mm-hmm. And so the way I understand our efforts at space travel is like you're taking off a trajectory to fall around the Earth consistently, and that would be called orbit. Yep. So if there is a bigger mass further out that we can get to fall around, we could pick up speed and we could arguably create a bigger slingshot environment around something, right? That's really where I was trying.
True. And in fact, I'll tell you something quite remarkable.
Okay.
That slingshot effect, in fact, is going on for, we think, the black hole in the center of our galaxy. In recent years, as we have surveyed our galaxy much better, we have found a very small population of stars, much less than 1% of the stars in our galaxy, that are absolutely screaming along at very high velocities, much higher than the general population of stars. We refer to these as hypervelocity stars.
Okay.
One of the main ways we think these are made is via a slingshot, where you have, for example, a binary star system that comes in close to, so you have two stars going around each other. They actually come in close to the supermassive black hole. There's a slingshot. The binary system, which originally had two stars, is broken apart. One of the stars becomes bound to the black hole. The other one gets tossed off into space at very high speed. And in fact, so this is happening naturally right now in our galaxy. You don't even have to have intelligence doing it. But in principle, if we could get to the center of our galaxy, we could utilize a slingshot effect there as well to achieve high velocities. In fact, stars are naturally doing that right now. Huh. And if you're interested in that, go look up hypervelocity stars and you can read all about that slingshotting.
I'm going to do it.
Yep.
And really, some of that is... and when my first question was talking about like exploring as humans in space, right?
Yeah.
The issue we face is we can't travel fast enough to get far enough in a timetable which we would live to enjoy the bounty of our journey, right?
That's the challenge. Yes. Now, you can, we may be able to put people in suspended animation of some kind, and that would allow it, but it's going to be a very long trip no matter what. That's the practical reality of things. That's just how big the universe is compared to how fast the speed of light, which is the very best case, limits us to travel.
Yeah. And that's where and the reason I was thinking about the black hole being a large gravitational pull and being able to get around it is the same principle that I would be thinking about, like trying to space or to planet hop almost, where you're using the gravitational force of the next planet, the closest one, to throw you towards
yourself up. That's right. Yeah. Yep. Yeah. And that sort of a slingshot effect, I mean, is a very practically useful tool. We've used that slingshot effect to launch space probes throughout our solar system.
Yeah.
So you could imagine doing that much better with a black hole. Absolutely. Even then, unfortunately, you're fundamentally limited by things like the speed of light. And it's a very tough thing. I mean, even no matter how you could hope to achieve some fraction of the speed of light, 10% the speed of light would be very impressive indeed. You're still talking about a very, very long trip. The universe is really big, and there's fundamental limits that light confines us to in terms of how fast we can hope to travel.
So that brings me to another subject matter that I think is in your wheelhouse, is the idea, and I don't know anything about it, so I'm interested to understand what X-ray astronomy is, and what are we studying? I mean, I know X-rays that go in, you broke a bone,
Correct.
it looks through your skin, it sees the hard matter of the bone, and it says, oh, there's your fracture. How do we use that and apply that in astronomy? I'm assuming it's the same technology.
Well, it is to a significant extent. It is, yes. Now there's a bunch of things I can say. So X-ray astronomy uses X-rays to study sources out in the universe. And X-ray astronomy turns out to be very useful, partially because of that penetrating nature of X-rays you just alluded to. The fact that you can see the bones in your hand, well, that makes it very useful out in the universe because we know that there are many cosmic X-ray sources, growing supermassive black holes, for example, that have a lot of obscuring material around them. Galaxies are full of gas and dust that prevents a lot of radiation normally from getting out. But because X-rays are highly penetrating, they often can get out where other forms of radiation cannot. The same way that you can see through your hand in X-rays, but you cannot see through your hand in optical light. Mm-hmm. Okay, so we utilize that penetrating nature of X-rays as one very powerful advantage to survey the black hole population out in the universe. There's a number of other advantages to X-ray astronomy. For example, X-rays provide a very large contrast between black hole related light and starlight. If you look at the universe in the optical light, you see all the beautiful light from the stars. And that's why galaxies look so beautiful when you look at an optical image of the universe. And you also sometimes see optical light associated with a growing black hole. But those two forms of light kind of compete with each other. If you look in the X-rays, the pictures are not nearly as pretty. You just see little point sources of X-rays, but almost all of that emission is from growing supermassive black holes. You have a very large contrast between starlight and black hole related light in the X-ray. And those basic facts, the penetrating nature of X-rays, the very large contrast between starlight and black hole light, make X-rays, for example, one of the best ways to survey the universe for growing black holes. And in fact, that's what I've done with a significant part of my career. I've kind of taken a census of black hole growth over the history of the universe, trying to understand how black holes grew over cosmic time, what physical processes allowed them to grow, and then how did they interact with galaxies. Those have been the kind of my bread and butter work for a long time. And so just in my particular research area, X-rays are really great. Now, I've just focused on my research area. X-rays are also wonderful for a wide variety of other science as well, studying stars that have blown themselves up. And in supernova events, you can study the remnants of these blown up stars called supernova remnants. You can do a great job studying those in X-rays. You can study stellar mass black holes and neutron stars in our own galaxy. We also find remarkably that most of the normal stuff in the universe, and by that I mean like the protons and the neutrons and the electrons, most of the normal stuff in the universe, leaving the dark matter aside, is actually in a form where you can most effectively see it in the X-ray band. It's in hot, diffuse gas. And so X-rays are very broadly usable in all the ways I've kind of described. Clearly, I tend to focus in on my personal research. They wouldn't build the Chandra X-ray Observatory just for my personal research area. It is a very broadly capable observatory.
Which again, we talk about misconceptions in the beginning. Tell me we're using X-rays in space.
Right.
Okay.
We are. Yeah, we've been doing it for decades. Yeah.
It's awesome. And I think, again, this is the objective of this entire show, is to bring light to what is out there, what's going on. So this has been awesome. But
great.
So if we use X-rays, and again, my simple understanding of medicine is you didn't break a bone. Okay, so the X-ray doesn't show anything. Then they send you to the MRI machine, the magnetic resonance imaging, and they're trying to look at everything that's not a bone. Do we have those types of use cases in space as well?
No, I mean, MRI, unfortunately, that's like a direct, probing mechanism where they use a magnetic field in your body. We do not have the ability to somehow send out magnetic fields out to a quasar and pull apart its structure that way. It'd be wonderful if we did, but again, the speed of light makes that type of thing very difficult. So we don't have the analogy of it. Probably somebody will correct me for some particular application, but in general, to my knowledge, we don't have the analogy of an MRI being used broadly out of the universe. Now, we do have, remarkably magnetized objects out of the universe. And the study of magnetic fields out in the universe is a fascinating and wide-ranging endeavor. And they're, and we find objects that have fantastically strong magnetic fields out in the universe. But in terms of probing cosmic objects using an MRI machine the same way, we don't really have such a thing to my knowledge. I mean, to my knowledge, no. Maybe there's some sort of natural analog to an MRI machine somewhere in the universe, but I don't remember any details of that.
Obviously, I mean, technology gradually advanced. Again, you say X-rays. I'm with Dave. Like, oh, X-rays in space. But if there was something that doesn't exist today, that 20, 30 years from now, what would we be looking to create to understand? Are there different types of like, if it doesn't exist, should we be trying to? Is there a certain field? Like, is it, hey, we understand that we can see this in two different ways? Yeah. Is there a third way we should try to be looking to create if it doesn't exist yet?
Absolutely. Yes. And astronomers and physicists have made enormous progress on exactly that type of thing over the years. I mean, so I'll just give you a brief historical perspective. I mean, one of the grand stories of astronomy and how astronomy has flourished over the decades now has been opening up the full electromagnetic spectrum to our understanding. Beyond that, however, you may have heard in recent years, there was tremendous excitement when people discovered gravitational wave emission from merging black holes. And the Nobel Prize was recently awarded for those discoveries. And so people are now studying the universe using gravitational waves. This isn't light coming to us. It's a totally different type of radiation associated with, the curvature of space-time predicted by Einstein's general relativity. So we are opening up our view of the universe now with gravitational waves, which let us study new aspects of the universe. We are also studying now particles from the universe, neutrinos, cosmic rays. Those give us entirely other distinct ways of looking at the universe. So I mean, the grand sweep of astronomy has been opening up new, different ways to look at the universe. Now, we've been pretty successful at that. That's been a good, probably now we're going on a 150-year ride. Okay. Now there will be limits when we've opened up all of the windows, and I think there's still a long way to go in all of them: electromagnetically, gravitational waves, particle astrophysics. We're making a lot of progress there. We've managed to open all those windows now, at least at a basic level. Electromagnetic is actually quite well developed, but gravitational waves and the particle stuff is much earlier in its development. And there's a room for tremendous progress in those ways in the coming decades.
That's awesome.
But that kind of progress plays out over decades. That's not something that plays out over months. Right. I mean, getting gravitational waves, there was a big press release when the first things were discovered, but there were decades of effort that underlay being able to do that at all.
Well, and I mean, it's much like the Mars rovers that were launched in like 2002, and we didn't get a look at them it was like 10 or 12 years before they actually landed, right?
Yeah. These things are and building them and designing them to start with.
Sure. Yeah.
Yeah. These are long time span endeavors. Yeah.
It is awesome. I could pick your brain about this stuff for days.
I can go on forever, probably. Yeah.
I think this has been a great overview of the types of expansionary thought. One final question I have is sort of on, we talk about natural resources on planet Earth. Obviously, our natural resources are infinitesimal compared to the resources that exist in the universe, solar system, all that stuff.
Yes.
Is there a focus or a discipline on trying to figure out how to harness those natural resources from outside of Earth to help us better our environment?
Yes. So there are a number of things there. One example is it involves near Earth objects. Mm-hmm. There are small bodies in our solar system, asteroids and such, that actually pass rather close to Earth from time to time. Mm-hmm. People have a desire to capture some of these and mine them. Asteroid mine them. You could put them into an orbit around the Earth and then mine them. And I mean, some of these have trillions of dollars worth of resources in them. And, unlike the Earth, where these resources are often buried way, way, way down and are hard to get at, these asteroids, it's not that hard to get, at least get down into them. Now, clearly they're up in space, and that's a great challenge. But
there's another complication. But
people who think on timescales of decades, have a great interest in asteroid mining and making space, which so far, just being honest, has not been a commercially successful endeavor. Yeah. It has not paid for itself so far. But making our access to space a commercially viable endeavor, and that would clearly benefit people by all the resources that are gained, and would also benefit astrophysics because it would give us real motivation to improve our launch facilities and things beyond where we have so far.
I mean, again, look at Elon Musk, you look at Richard Branson and these guys that are actually taking their own personal wealth and now investing in it. If there is actually a gain, you now thrust money, brains, power, and the private sector into that arena, which is a whole different ballgame, which who knows how fast it could increase.
That's right. Yeah. And so there are people who are thinking about that extensively. One of my old mentors, a man named Martin Elvis, in fact, has written a nice book on this topic, as well as broader issues if you have interest.
I do.
So you can check out that book. I'm happy to give you the reference later on. And in addition, of course, there are other places in the solar system where there are valuable resources. For example, people have interest in going to the moon or Mars long term. You may have heard that just over the past week or so, there's been a successful landing by the Indian government on near the south pole of the moon. One of the reasons they're interested is there's quite possibly water there, and so they're prospecting for the possibility of water down there. And similarly, there's interest in tracking down where there might be water on Mars. And this is an essential basic ingredient that is needed to sustain a long-term human presence in one of these places, which could then be used ultimately for resource extraction. But again, this is going to be a decades ball game.
Yeah, for sure. The long game is at play.
Yeah, but there are good prospects there. Again, these asteroids could have trillions of dollars of valuable metals in them, including metals that we need for like semiconductors and things that we don't have easy access to. Yeah.
And that is plausible for all intents and purposes. It is plausible to create the system to attach to it, to get it to either slow down or fall into orbit and give us an opportunity to work on it essentially.
On a time scale of decades, I think it's plausible. I wouldn't expect it in the next decade, but on a long time scale, in a long time scale, I think it's quite plausible. Yes. And again, if you want to see, I don't play that game for a living. But if you want to read more about that, again, I can give you a reference by a very smart man who has spent a lot of time thinking about this in recent years. He used to be an X-ray astronomer primarily, and then he kind of jumped fields and thinks about these things a lot. Yeah.
Oh, I would love to hear it. And again, we're winding down now, but if you know any other professors or any other your colleagues that would love to share what they do and talk like this, we'd love to have them because this has been a fantastic conversation.
Yeah, I'm happy to give you suggestions of colleagues who might be happy to speak with you. Yeah, sure.
Cool.
I mean, Martin Elvis might be happy to speak with you as well.
I would love it because I would that conversation I'd love to hear.
Okay, great.
But we're about out of time.
Sure.
Professor Brandt, I want to thank you for your time. This has been awesome.
Of course,
everybody listening, this has been College Knowledge, and we interviewed Professor W. Nielsen Brandt, the Eberly Chair, Professor of Astronomy and Astrophysics at Penn State University. Thank you for your time.
Very good. Thank you for having me.
Thank you guys for being a part of College Knowledge. You know your support means everything to us. Please leave us a review and help us grow and help more families. Thanks for listening to the College Knowledge Podcast with your hosts, Dave Kozak and Joe Kearns. We hope you enjoyed this week's exploration of higher education, sponsored by the College Planning Network and Paradigm Financial Group. That's all for this episode. See you next time.